did play with Fibonacci's for a few minutes last night.
Was there no time to
So what? Yeah, this was. And I was trying to prove this idea that fn squared equals fn plus 1, fn minus 1, plus or minus 1. And I got out the fan-fold paper and started working on it. I didn't get much time to work on it, but in trying to prove that, I came up with two other things, which I assume are well known. But I couldn't prove this inductively, so I was trying to show this for n and then assume it for n and prove it for n plus 2, and I kept kind of just sort of pushing the problem back but not getting any closer. But I did change this down into another problem, which was to show that this is true. The difference of the squares is within one of the product of two consecutive Fibonacci numbers. So 25 minus 9 is 16, 5 times 3 is 15. 9 minus 4 is 5, 3 times 2 is 6. 64 minus 25 is 29, or 39. 8 times 5 is 40. And that's provable, given this. The other one, which I didn't prove, but I noticed, was here's the one that I think is different from the one we just did downstairs. But 64 minus 9 is 55. Which is 5 times 11. That's close. So this squared minus this squared is equal to this times the sum of these. So 13 squared is 169 minus 25 is 144, and that's equal to 8 times, that doesn't look right. This thing squared minus this thing squared is equal to this thing times that. But I don't know why that's true. But yeah, the difference of two squares is equal to the one in the middle times the sum of those two. Yeah.
With the behavior you had trouble proving, do you think it's possible that the reason for that is because of the way that it alternates, and that maybe it would be easier to prove the positive and prove the above and then prove the below?
Yes.
Yeah.
I do believe that. So that's what I was trying to do at the end.
Yeah.
Would show it for n, given that it's true for n minus 2, and I just used the case where it was always plus 1.
Right.
But I could change it into equivalent things like this, but the polynomials that you start coming up with start having coefficients that look like Fibonacci numbers, which is a little worrisome. But kind of comforting at the same time. Yeah. Alright, so anyway, fun stuff to play with. sure if you go to the wiki page, it'll tell you all about this, but I didn't want to do that.
All about your grand discoveries.
Yeah.
That's what I used for my programming assignment.
Wiki page?
I used the Wikipedia article for the binomial coefficient.
Mm-hmm.
They gave me a really, really good recursive
Okay,
formula
cool.
for the coefficient.
Cool. Yeah, so Pascal's triangle, there's two ways to do it.
How about NCR?
Right, one way is to write a loop, store all of the elements of a row into an array, and then create an array for the next row by just adding successive pairs. So 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and just stick a 1 at each end. Or start with an array and always have zeros on the end. And now we don't need to do something special with the 1. 0 plus 1 is 1, 1 plus 0 is 1. We just need to pad zeros on the end. And when we print it, just print the middle stuff. But the other way is to use combinatorics, right? To note that this is an R in row N, column R, and use the factorial formula for that to generate the entries for each row. And it's interesting because to do it like this, all you have to do is addition. To do it like this, you got to do a lot of multiplication, and it feels like a very different amount of work.
But that's also really easy to code.
This is really easy to code. It's
That
really
always-
easy to code if you can deal with the big numbers.
Yeah.
But you can't just, for example, take 100 factorial and divide it by
Yeah.
50 factorial and divide that by 50 factorial.
I
You either
use-
got to be tactical about multiplying and dividing at the same time so your numbers don't get big, or use long longs.
Because what I did was
But don't ask
I
for
used
23
longs.
rows.
I used longs and went to 20, I think, was,
Yeah.
where it got to.
Okay.
Before it broke down. 21, yeah, 21 was what
Yeah.
it was. And I'm sure an unsigned long would work
Yeah,
for longer and all that, but
And there's ways to do unlimited arithmetic in C. There's libraries that do it character by character.
BIGNUM. Big Num
Bigum.
Libraries, that's the name
Oh,
for
big
those things.
yeah.
You said n rows are columns, right?
N is the row number and R is the column, I believe, yeah.
yeah.
And you just have to be careful where you start from. Yeah, there's a Unix command called BC. I think it's binary calculator, but it's not actually binary. But it does like really big numbers.
Wow.
So then could we bundle in a system call or something?
Yeah, you could. So there's to the 19,937.
And you're saying it's doing this
Try.
character by character? That's how
Yeah,
that's how
yeah.
it was?
It's doing basically pencil and paper add and shift
Wow.
kind of operations.
That's crazy.
But you can get like really big numbers.
Or if you just get an API called Wolfram Alpha and have it do that.
Well, yeah, you can go to Open Alpha too.
Yeah, just pile in a network library. That won't take up more than a few thousand lines and see.
That's never gonna.
Oh, that's right. That's right. System. I keep forgetting.
Doesn't even understand Control C.
You really killed it.
It's like, don't bother me, I'm thinking.
We'll just let that stew
We'll just
for
let
a
it
while.
sit there.
Yeah, in like 3 days, so we come back.
Which process is using right now?
Control Z usually like gets it good. Yeah, so BC is available. All right, let's keep talking about Boolean things. So identities. The complement of x is equal to x. That's double complements or double negation. These are called idempotents. x ORed with itself is x, x ANDed with itself is x. And we use these things a lot, and we don't even bother acknowledging that we're using them, because they're pretty obvious, but we do use them to do a lot of other things. X ORed with 0 is x, x ANDed with 1 is x. Those are the identity element. So 0 is the additive identity. When we add it to something, it doesn't change what we're adding it to. And 1 is the multiplicative identity. When we multiply by 1, it doesn't change what we're multiplying by 1. We have commutivity. So the order doesn't matter. And we have associativity. So we can group things together and do those groups in any order that we want. And we have distribution. These are called absorption. So we're absorbing the y variable, basically. Because if x is true, this expression will be true. If x is false, then xy is going to be false, and the whole thing is going to be false. So we can throw away the y. And similarly here, if x is true, we know both of these will be true. And if x is false, this will be false, and so the whole thing will be false. So the y is irrelevant. This wasn't on my list, but it's my favorite, adjacency. So xy or xy bar is the same as just x. But we can actually get that from these other identities. X or x bar is 1, x and x bar is 0. That's just unit property and zero property. And this distribution we know from algebra, right? We do that all the time when we're expanding equations. But this one looks kind of peculiar. And algebraically, it doesn't make sense. Because this is x or y, z, but over here we have x or y ended with x or z. And algebraically, it would be x squared plus yx plus zx plus yz. And that looks different from here. But if we go ahead and we distribute, which is all that FOIL is doing, we get this. And we we know that x ANDed with x is just x, that's idempotence. And we know yx is the same as xy, that's commutivity. And we can factor out an x from these two terms. That's just the reverse of distribution. And we can absorb this term because this is x or x ANDed with something else. This is just x, that's absorption. And so we see that in fact this is the same as x or yz. But you gotta use a half dozen of these other properties to actually get there.
It also looks like you're just distributing the x as well as the or operation to both the
Yes.
y and z.
Yeah.
Which I guess is kind of easier to remember.
And there's a way to generalize that observation, which is all of these things come in duals. They come in pairs. And if we exchange ands and ors, and we exchange zeros and ones, we usually get another rule that's also true. For example, I changed this and to an or, I changed this or to an and, I changed those ands to ors, I changed this or to an and I got a parallel identity, a dual identity. Here we changed our or to an and our 0 to a 1, and we got another identity. And in general, this always works. And it's because these things come in pairs, right? They always move around together. And that can seem mysterious, especially to a Western mindset. Why do we always have this when we've got this? Why do we always have this when we get this? But it's really not so mysterious because they're actually both saying exactly the same thing. We're just representing one fact in two different ways. And that theme permeates a lot of digital logic. When we look at sum of product versus product of sums, they look like similar processes. You just change this and twist this and you get from one to the other, or you can go back. But they're really the same thing. It's the same process. We're just interpreting it in two different ways. When you do KVL, KCL, and 120, it looks like we have two separate processes, but it's the same analysis technique. We're just viewing it from two different sides. So we see these duals pop up in computer science, we see them pop up in engineering and physics and all over the place, and it can be instructive to think about them maybe not as being duals, but as just being two views of the same thing. And we'll play with Minecraft a little tomorrow, and I'll hit that point again.
Could you explain the absorption step a little bit again?
Yes.
Second to last.
So, you mean up here or over here?
How you did that stuff.
Oh, absorption says x or x ANDed with something is just x. And the logic is if x is 0, this will be a 0, and this will be a 0. And this will be a 0, so it'll be an identity. And if x is 1, then that alone makes this term 1, because you're ORing with a 1. And x is a 1 over here, so you'll have an identity again.
What would be 1 plus y?
Doesn't matter what y is, though. 1 plus anything is 1.
This is
Right? It's an
Boolean.
or of bool,
It's or.
an or of true with anything else.
Oh.
Right? So the or is true as long as one of these things is true. So we can ignore the y in either case. And then over here, the y is just this thing in parentheses, so absorption says we can ignore that whole term. And you can do it in the truth table too, and verify it that way. Oh, and I forgot the Morgans. Alright, so there's Morgan's theorems. And that lets us move from ands to ors and back the other way, which is often useful. And it's really at the heart of a lot of what we're going to do next, which is looking at expressions coming from truth tables. Give me one sec. So if we have an expression right, we can make a table to describe the value of this function at every possible point. So this is listing all points in B cubed, a set of 3 tuples, coming from the universe of 0 or 1. And we can list the value of f in each of those cases. And so if x and y are both 1, then our function will be 1. And if x is 1 and y and z are both 0, our function will be 1. And it'll be 0 everywhere else. And so we use truth tables as another way to represent a function. And you're just exhaustively listing what the function maps each point to. But the interesting question is, if you don't know what this function is, but you know the truth table, how do you find a function that gives you that truth table? And there's 2 approaches we typically use. And we can motivate each of these intuitively, but one of them generally feels more intuitive than the other, like LDL, KCL, bless you. So here's the first way to motivate this. We want to find an equation, f, that's equal to 1 when your inputs are like this, 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 or this, right? So we try to find an expression that captures the fact that, for example, x is 0 and y is 0 and z is 0. And we have an AND operator. I just said AND twice, so that's a hint to use an AND. And ANDs tell you when things are 1. So if we want to know when x is 0, we can say, how about telling us when x bar is 1? So if we say x bar is 1 and y bar is 1 and z bar is 1, that's only going to be true if x is 0, y is 0, and z is 0. And down here, the expression x bar, y, z will only be true if x bar is 1, y is 1, and z is 1. And if x bar is 1, that means x is 0. So this equation is true only if x is 0, y is 1, and z is 1. And similarly down here in the 6th entry, if x is 1, y bar is 1, and z is 1, then x, y, z must be 1, 0, 1. And in the 7th entry, x, y, z bar will be true if and only if x, y, z is 1, 1, 0. And so we can generalize this and we can call these min terms. And for each row of our truth table, we can write an equation that's true exactly when x, y, and z correspond to the values in that row. So x bar, y bar, z, x bar, y, z bar, x bar, y, z, x, y bar, z bar, x, y bar, z, x, y, z bar, and x, y, z down at the bottom. And now I've got to start drawing more lines. So to write a function for f, so let's try to keep the parallels. So we represent these minterms with lowercase m's, followed by the row number, where we start from row 0, 1, 2, 3, 4, 5, 6, 7. And the row number is just what this number is in decimals. So this is the number 4, this is row 4, this is minterm 4. Okay, here's the intuition. Minterm mi is equal to 1 if and only if x, y, z correspond to row I. And we got to start from row 0 for this to work. So if I look at M5, it's going to be 1 if and only if x, y, z correspond to row 5. In other words, x is 1, y is 0, c is 1. That's the only case where this term is going to be equal to 1. So we can use that to write our function f as follows. So write f such that f equals 1 if x, y, z correspond to rows. In this case, I'm going to do rows 0, 3, 5, or 6. In other words, rows 0, 3, 5, and 6. I want my function to be 1 in exactly those cases. Anytime that x, y, z correspond to the values here, 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 or here. Well, I know how to write a function that's going to be equal to 1 exactly if I'm in row 0. It's just m0. And I know how to write a function that's going to be 1 exactly when I'm in row 3. It's just m3. And similarly m5 and m6. And I want f to be 1 if I'm in this row or this row or this row or this row. So I can just OR those. And there's my function. So we learned that in 120 and we use it mostly in 250. And it's just called the sum of products. And the minterms are products. ANDing is considered multiplication in Boolean algebra. It's the multiplication operator. So these are product terms, and ORing is considered summing. It's the addition operation. So this is an OR of ANDs, a sum of products. And that's the version that we first encounter in 120, and it's the one that sort of rings most naturally. But there's a dual to this.
There's always a dual.
Always a dual, the famous POS. So instead of minterms, I'm going to write max terms. And they're just written with an uppercase M. So for sum of products, we wrote the min term each place that the truth table should have a value of 1. Each time our function should have a value of 1. And we ORed them together. And in words, what we were saying was we want our function to be 1 if we're in this row, or this row, or this row, or this row. Okay, here's the dual way of looking at it. So, write f, so f equals 1 if we're not in row 1. So if we're not in row 1, if we're in row 1, our function is going to be equal to 0. The cases where our function will be 1 is if we're not in row 1 and we're not in row 2 and we're not in row 4 and we're not in row 7. Exact same function. We're going to write a function that's equal to 1 if we're not in this row, and we're not in this row, and we're not in this row, and we're not in this row. Because if we're in any of those rows, our function should be 0. If our function's 1, we're not here, we're not here, we're not here, and we're not here. Good so far? I see suspicious looks, that's good. So let's write an expression that's going to be 1 if we're not in this row. And this is going to turn out to be M1. So max term Mi equals 1 if and only if x, y, z don't correspond to row I. So how do we write an expression that's 1 only when we're not in this row? So if we're in this row, x is 0, y is 0, z is 1. So if we don't want to be in this row, what can we say about x, y, z?
They're not 0, 0, 1.
How else can we say that?
So they're 1, 1, 0?
That's one possibility. How about 1, 0, 1? That's not the same row. How about 0, 1, 1? That's not the same row. 0, 0, 0, that's not the same row. If any one of these is different from 0, 0, 1, we're in a different row. So let's say M1, we're going to be in a different row if x is not 0. In other words, if x is true. Or if y is not 0. That'll put us in a different row. So if y is true, we're in a different row. Or if z is not 1. In other words, if z bar is 1, any of those three cases, we're in a different row. So this max term is an expression that's equal to 1 exactly when we're somewhere other than row 1. Okay, so that's our max term. Mi is equal to 1 if and only if x, y, z don't correspond to row I. So if we want to find a function that's equal to 1 in these cases, we want a function that's 1 when we're not in this row, and we're not in this row, and we're not in this row, and we're not in this row. Well, an expression that's true when we're not in this row is just M1. So if M1 is true, and M2 is true, and M4 is true, and M7 is true, then we're not in this row, and we're not here, and we're not here, and we're not here, so our function must equal 1. So that's an equivalent expression for an equation that's equal to 1 in the places where this truth table shows 1. And it's the exact same process, it's just a dual. Here we said we want this to be a 1, we want to be in this row, or this row, or this row, or this row. By looking at the 1s. If we look at the 0s, we don't want to be here, and we don't want to be here, and we don't want to be here, and we don't want to be here. So we write it as an and the expressions, these max terms, are the things that are true when we're not in this row. With the sum of products, we write it as an or, and we write min terms, which are true when we are in this row. So this is the product of sums. Does that make sense? It's probably taken me 2 years to really sort of get warm and fuzzy with this. And I'd say I'm warm, I'm not quite fuzzy yet.
Wait, how long have you thought you'd be for?
Oh, I think 4 or 5 years.
That's comforting.
Yeah. KVL, KCL was the same way. It took me like 2 years to really sort of come to grips with it. Yeah.
The reason that you'd be interested in one over the other is that one could be shorter logically, correct?
Correct.
Okay.
Yeah.
Yeah. To create in a circuit, I mean.
Mm-hmm.
You can use De Morgan's to go between them, right?
And you can. This is really just De Morgan's theorem. Thank you. This is just De Morgan, right? When we say if we're in here, then x bar and y bar and z bar. If we say we're not in here, we're saying x or y or z. Right? Those are the same things. Right? That's De Morgan's theorem connecting them. When we do a sum of products, we write this. When we do a product of sums, we write this. So your max terms and min terms are just duals to each other. They're connected through De Morgan. That's not.
That would just be x or y or z, I think, not the column.
Yeah. Right.
Do you know why they're called max terms?
Just want to ask that.
There's probably a good reason.
Max versus min, yeah.
Max.
Because if any of these is a 1, this becomes a 1. So it's the maximum of the 3 values, maybe. Whereas if
How about that?
all of these are 0, if any of these are 0, then the whole thing is a 0. So it gives you the minimum. That's a guess.
Suddenly makes sense.
Yeah, and that's theory.
Whether or not it's true, it makes
I know.
sense.
But there's probably other reasons. All right, so yeah, De Morgan's theorem really connects sum of product of sum, and I feel like I should be saying something else here, but I can't think of what I could say. Yeah, there is a bar here, because our relationship is like this. All right, completeness. So any truth table that we can write, we can express as either a sum of products or a product of sums, using either of these techniques. Which which means that if we have in our repertoire and, or, and negation, we can write any Boolean function. Because that's a sufficient alphabet to write a sum of products or a product of sums. And any function that you can express as a truth table, we can write an equation using sums of products, for example. And so this is a complete set of building blocks. It's functionally complete. But it turns out
There, makes everything easier.
that just having ands and complements is also functionally complete. If you can do an and you can do a negation, you can do an or. Because I can say x bar, y bar, and that's equal to this, which means if I take x and I complement it, and I take y and I complement it, and I and those and I complement that, I've got an or. And if all I have is an or and a complement, I can say x or y bar equals x bar anded with y bar. And if I take x complement or y complement and I complement that, I get an and. So if I have these, I can get my and. If I have these, I can get my or. And it turns out that if I have nothing but a nor, I can get an or and a complement out of it. I can get an or by, well, I can get a complement by just noring something with itself. And if I have a nor and I have a complement, I can complement my nor, and that gives me an or. So all I need is a complemented or, and I can get everything else. I can get ands, nands, ors, nors, complements, exclusive ors, random functions, yups, nopes, everything else.
Does this follow for NAND?
This follows for NAND also, yes.
And then more of the universal gates.
Yeah,
They're also not found in organic, you haven't even.
yeah. But in the 60s, when NASA and the country were trying to go to the moon, and they were trying to build computers, and there weren't commercially available integrated circuits, they had to build integrated circuits themselves. And you could build AND gates and OR gates and inverters and all the parts that we have in our parts box next door, but they took a different route. They decided to build a single chip. They built NOR gates. And they used combinations of those to get all the other logic functions.
We went to the moon on Norgate.
We went to the moon on NOR gates.
Was this like in the ship or
Yes.
at the command center?
This was in the ship.
Wouldn't it have been better to like
It would have been lighter.
optimize it for weight?
Sure.
It would have been lighter, but the thing is, it's easier to do the same thing over and over and over and over
Right.
and over again than
Yeah,
it is.
but-
And reliability was a big concern. And every time that you design a new chip, they had to go through a whole vetting process to check its reliability and durability. And the decision was made that we'll just go with a single component and we'll build lots of them.
And
But they were
building a lot of one thing is a lot easier than building a few of
correct.
many things.
And these were integrated in silicon, so it wasn't discrete chips being put together.
It's like put it latches.
Yeah, so these are latches, these are flip-flops when they're cross-coupled like this, and some of them are just random logic. So this is part of the Apollo guidance computer, and you can find those schematics online. They've been uploaded, and it's just NOR gate after NOR gate after NOR gate.
Also,
It's wonderful.
NOR gates and NAND gates are cheaper because in CMOS you have to add an inverter.
Right.
So it's 4 transistors versus 6 transistors.
Perfect. So yeah, when you actually make these things out of transistors, the first thing that you get is an inverted output. And if you want an uncomplemented output, you have to add more logic.
I actually thought it was interesting that NASA doesn't use the newest technology available.
Yeah.
They send something up in space. It's like I almost want to say a decade, but at least a few years before, and before they sent it,
Mm-hmm.
when it was, the up-to-date one.
Yeah, that's often true, and it's even worse because by the time their machinery gets to where it's supposed to be, it's often been another 10 years.
Yeah.
And even if they put like that day's technology on, it's like a decade out of date by the time it deploys.
Well, I was just
So-
reading about the EM drive that NASA's working with
Oh,
right
yeah.
now, which is super crazy
Mhm.
technology, but that was designed in 2001, and they
Oh,
just
wow.
got around to testing it now.
Yeah,
And that's this whole thing where it's propellantless thrust
right.
with no reaction, which
Yeah,
is like
That's awesome.
going against all the laws of physics that we
Yeah.
don't understand.
Very cool.
It's super interesting.
Don't they have to worry about like radiation and the
Oh,
smaller
yeah.
your,
Oh, yeah.
Yeah.
the smaller your gates are, the more you have to worry about radiation.
Yeah, so these worked at a higher voltage than what our phones work at, for example, which would make them more immune to upsets like that.
And
But
that's
yeah,
actually,
there's a lot of science about radiation hardening components and so on. We're out of time. If you got a scoot, you can scoot, but I'm gonna be here anyway.
I was gonna say that's the big problem that they're countering with this EM drive thing that they're working on right now is it's microwaves and I think electromagnetic fields that making this work.